Hi everyone, today I'll tell you what is the black box attacks and why it was dead and why it's alive now. I will tell you about now ATM research related to cash dispenser, one of the main parts of ATM. Also I'll describe how it works, its hardware security, how to get money from an ATM, and how the successful attack can be performed. This research will be done together with my colleague Vladimir, but he couldn't come. So I'll tell you about it. Let's begin. So, who we are? My colleague Vladimir, his job and his hobby is reverse engineering. He works in positive technologies research team. He started reversing in 2008, and there was different correctness, keygamings, and so on. Also, he is an active Sega Mega Drive or hacking community member. He helps others to translate different old-school TV games to their foreign languages and modifying them. My name is Alexei. My previous job and my hobby was hardware engineering and embedded systems software development, including industrial control systems. I'm also interested in hardware and software reverse engineering. Now I work in positive technologies in industrial control systems, security research team, and execute some work on ATM projects. So, what is the ATM area? Actually, it's a very closed area, and it's difficult to get into in. It happens because the vendor's main idea is to make security through obscurity. Actually, you can find any software development kits, software samples and firmware in public. But real ATM is almost the same as you can see in the picture. It's also hard to take an ATM to research. What you can find inside ATM? First of all, it's divided into two main areas, upper cabinet and the safe. Then the cabinet is opened, you will get into service area. The following ATM parts located here. It's PC, monitor, encrypting pin pad, printers, uninterruptible power supply unit, and other devices. All devices connect to PC just like usual peripherals. Usually logical attacks can be done through this zone, because most of locks in cabinet are primitive. The most interesting device is the dispenser. Its purpose to store and issue cash. Therefore, it stays in the safe. The only accessible in service area things of dispenser is power wires and bus which connected to PC. Let's look at the data flow of ATM. It's not complex. External communication of ATM is a communication with the processing center. Processing center communication realized using VPN, TLS, and other secure things. And it's secure in most cases. The next level is communication Windows-based application. It communicates with XFS services layer by an API. It's middleware which implements unified device access. Service provider is bottom layer solution for interaction with devices. The lowest level of communication is the data transmission over hardware buses to devices. We are interested exactly in this issue. Some people want to take money from ATM because it's a box of metal and plastic. The main ATM security threats are fraud, brute force attacks, malware, and hardware attacks. ATM crime actions can be divided according to the method of access into two main parts, physical attacks and logical attacks. Let's look at each of them. Physical attacks can be fraud-based or brute force. As you could hear from the news, this kind of attack is widely used, most popular, and happens everywhere in the world. It uses trivial techniques like schemes of different complexity, trappers that hold the card inside ATM, cameras, and some transaction reversal techniques. Another type of physical attacks is brute force attacks. For example, intruder can blow explosive gas to the safe, then detonate it so that safe door will be turned out and stored cash will be scattered on the floor. Another example is arresting an entire ATM from a wall by a truck. The results you can see in the pictures. Now let's look at logical attacks. The most common type is malware-based attacks. There are many ATM-targeted malware, but they all use XFS layer to interact with hardware parts, basically with dispenser and pin pad. If you are interested in ATM security, you may hear green dispenser, concrete maker, plotters, and other malware. There are few distribution ways of such malware, remotely from processing center or locally from USB device, for example. Now let's look at another type of logical attacks that's called black box. It's one of the most complex and technically difficult attack, but it has many peculiarities. Black box attacks are attacks with usage of some extra hardware devices connected to hardware bus. These devices are called black boxes. You can see an example of such device on the photo. To the casual observer, it looks like open service area connecting some device or laptop to dispenser bus and cash withdrawal. Thus, this type of attack requires low-level protocols and hardware of ATM knowledges. Such attacks do not depend on processing center, operation systems, and other software. Let's try to figure out how to connect the dispenser to the PC. Generally, it's connected by RS-232, SDC, or USB interfaces. Also, in some sources, there are references to CAN bus usage, but we haven't seen it a live project. Let's take a more detailed look at these devices. The first and the oldest device is RS-based RS-232, as well as the COM ports. The specificity of this connection is the usage of multiplexer to expand the number of ports, as there are usually not enough in PC. An example of multiplexer is in the photo. You only need a laptop and cheap USB to COM adapter to perform this attack. Usually data transmitted in an unprotected, clear way, and firmware encryption patches are very limited in their resources. In a number of cases, the commands are human readable, and it's enough to look into the traffic in order to understand and reproduce them. This is too primitive, so let's move to the next interface. This is the SDC bus. It's proprietary for NCR ATMs. In fact, this is RS-485 is a multi-drop COM port. The vendor uses unusual bitrate and byte size here. The encryption is trivial logical XOR operation. The interaction is built on principle of master several slaves. Devices are connected to the same wires of the bus in parallel. Please remember this fact. A popular attack of this bus called drill box. An attacker cuts hole in ATM fascia next to the pin pad. Then attacker turns off pin pad, turns on his device, connects to SDC bus, which also goes to the safe for the dispenser. Further, you only need to send data protocol sequences for cache action issue. Usually a special interface card installed to PC for communicating over SDC. And finally, the most interesting and most complex logical bus is USB. First of all, you need to understand a lot of terminology, a lot of abstractions. For example, endpoints, descriptors, the interfaces, and their types. Typical dispensers are identified as human interface devices or composite devices. However, to see the data at low level, you need a hardware sniffer. They are usually expensive. Obsolete USB dispensers, they are usually inherited protocols from COM port devices with the same drawbacks, but we will not consider them. Let's look at examples of real attacks on more sophisticated USB dispensers. One of the findings of the Positive Technologies research team in devices of this type in 2014 was incorrect initialization of random function, so the initial key was predictable. In this regard, a poorly implemented encrypted protocol appeared to be vulnerable. This error allowed to iterate the session encryption key for finite time, and then to send a command to issue cache. This vulnerability was fixed by the vendor. The most recent attack attributed to attacks of this type was made in 2017. In addition to get this laptop with engineering software, which dispenser was connected, and endoscope was used. Through the hole, when the shutter was broken, an endoscope was laid down into the safe. We switched the sensor by simulating an authentication of the engineer during maintenance. Thus, firmware of dispenser function cache issue test was unlocked, which was used by the attackers. At this point, it could have seemed that black box attacker think of the past or died as a class, since the last attack refers more to physical attacks, and manufacturers have implemented encryption everywhere. However, we proceed to our case. So, to research ATM hardware, we need to determine the manufacturer and hardware. In our case, the choice was quite simple, since the NCR is one of the largest of ATM vendors and software for them. And it's also very common on our Leaf projects. New ATMs are considered one of the most secure, and communication with the dispenser are encrypted. So, our choice is a dispenser with NCR as one controller. Usually, cache dispenser is a very complex device. Mechanics of dispenser performs cache storing, picking, validation, and transportation. Every movement is performed by drive units and controlled by sensors. The brain of cache dispenser is its control electronics. They are usually called dispenser controller. All mechanical parts of dispenser have their specific names. The dispenser are built with 2 or 3 or 4 PIC modules placed below dispenser model. Presenter model, sorry. Bills are stored in the cassettes. Also, the dispenser has dedicated rigid cassette for jammed or wrong PIC banknotes. Bills are transported from PIC mechanism to a bill validator and then to presenter. In case no error have occurred, banknotes are issued through the shutter. Dispenser controller is a control board that controls the operation of currency dispenser. It's called fire processor-based board, responsible for collecting all sensors information and operating the mechanics, and also communicating commands to the PC. The control board is a mixed technology PCB employing both SAS mount technologies and plated through the whole components. The function of control board you can see on this slide. So, you want to protect your future, you want to find and report some vulnerabilities to NCR, but you don't have an ATM and you also don't have firm binary. What to do? Well, unfortunately for a vendor, unfortunately for you, it is possible. For example, you can order the dispenser controller at eBay, but how is this possible? Well, when something breaks in the dispenser, service center usually replaces the whole device. Now somebody can sell a broken dispenser by parts. After you have bought a dispenser controller, you need to get its firmware. It's much more harder, but if you have a friend in some service center, you can ask him. For most of our tests, we don't need full dispenser assembly. When you want to play with protocol and other basic logical features, all you need is controller board, power supply, laptop or PC, and USB connection cable. This slide shows brief information about the firmware. It works work-based. First of all, it's not encrypted. It would be much more difficult to analyze such file, especially if you can get access to the encryption key from PC software part. The second thing is the dispenser file has unstripped symbols. It makes our analysis less difficult. To start with, we must understand that in our case we have USB device. So the firmware must contain some code that is responsible for sending and receiving command packets. To find the code, we must find the CPU name on its chip And find datasheet document with the USB control register and data register constants. Here are some of the search results of those constants. As you can see, we have found write packet and read packet functions. You may notice that function names are mangled here. Unfortunately, I provoke and unmangle them. My guess is that it happened because of VxWorks compiler peculiarities. The first thing that we will face is going to an absence the public Motorola decompilers. Another thing will be C++ virtual function tables and virtual calls will be difficult to analyze in x86 too. If you divide the code into main components, you will get following scheme. The first level at red is responsible for receiving, distributing USB packets between services. Services is a basic execution units. Each of them has its own role and its own tasks. Classes here are tasks that are executable by different services using such thing as controller. Controllers is the logical things. In fact, they are workers who perform commands validation, execution, and answer forming. To execute an exact command, you must specify a class and a logical controller indexes. Before that command will be executed, the execute function, it will be checked with validate command function. Format response function forms the response packet with execution results. Dispenser transaction service is the most interesting service for us. It works with banknote withdrew command and their encryption. This service has 3 classes, but only 2 of them are most interesting. Class 1 works with the secure messages and second one works with encrypted secure messages. The only difference between them is what class 1 skips some more secure commands using reject array with command indexes. My guess is previously there was only one class. This code looks more like a fast fix rather than a good approach. On this slide you see the sequence of actions that needs to be taken to generate initial key. The first action is to select the encryption initialization command on service operating screen. Then you need to toggle the bottom cassette in the safe or to perform switching the special tumbler on the controller board, all within 1 minute. After that, the dispenser will send you initial key. Encryption keys have their role types. It means that every key for every message will be different because of the rolling component, like a session number. Okay, you think that it's possible to intercept the packet with the initial key and use it then? No, it's not. In the handle initiate key exchange command, the PC also sends the public key, which will be used to encrypt the initial key. Another part of the command is the hardware ID, which must be equal to real one. That makes brute forcing of this command impossible. Unfortunately, we haven't the physical access to the safe where the dispenser controller is located, so we cannot perform the initial key exchanging. It's only possible in the protection level parameter was set to USB or logical one. To downgrade protection level from physical one, you also need to have physical access to the safe. So what should we do? Surely there is a way how to PC download the firmware binary into dispenser. Usually such things are called bootloaders, and we must find it. Sometime later, we found the service that is responsible for switching to bootloader, and its name USB is download service. The only things that it does are switching into bootloader and sending a USB device information like a vendor ID, product ID, and packet size to us. The most interesting fact is that commands of this operation don't require to be encrypted. The bootloader itself has been hiding from us for long. Its code could have found by string search or function name search. We have found it in data section in the form of that lib stream. Actually, the secure word in its name is a fake, because there is no any secure things in it. This part of research was the most difficult. We have reprogrammed the NVRAM chip a lot of times. So I'll still decide to make firmware download research. You must understand that without NVRAM backup, you have many chances to break your device. So what you need to do is to fix your firmware binary according to your intents, surely for research. The first action is to switch into a bootloader. At these steps, the special flag will be set in NVRAM. It will be checked at firmware boot. This flag was the cause unbootable firmware during our attempts. The second action is to generate a key pair for signage check that will be performed later. Self-signed firmware is a popular phenomenon, but it's fully useless in our case, because it won't help you to protect the firmware if you are able to change public key. You may specify the controller serial number and the version of the firmware. At third step, we need to send the reboot command. The dispenser bootloader will be booted again. The next action what we need to perform is the send data in and text section sequentially, specifying physical addresses and size for every block in the packet header. Here are the problems we encountered. You cannot just write a changed block. You must write the whole firmware sequentially. Also, you can specify virtual addresses here. You have to specify the physical ones. At this moment, we must already have the SHA-1 calculated hash for uploaded bytes and encrypted with the private key or the key pair that was generated at previous steps. Also, we need to calculate the sum of written half words. At the first step, we must send the signed hash so that the bootloader will check the data was sent before. If signage validation fails, you will get brick again. The sixth step requires sending calculated checksum and the physical addresses with firmware bytes downloaded. Here there were a few problems too, because I couldn't find a check for the physical address field, and it led to brick device many times. And we have another attempt. And finally, the current firmware successfully downloaded and we were happy. But could we download some old firmwares with the old vulnerabilities? And we tried to do that. And this appeared some more problems. There was checked that the downloadable firmware had same or greater version number than in current firmware. This check can be skipped if no physical access was set. But it's not possible for us. But luckily, when I added availability to upload any firmware binary, if its version equaled 4F in hex, money withdrawal was still a problem. Encryption function was professionally implemented, so we decided to fix secure command function so that it could allow execute any secure commands without any encryption. To do that, you just need to make move 0 to D0 in assembly language and then perform return call. To sum up, we have an ability to not use the cassette or tumbler switching. We can patch every byte in the firmware, and now protection level is not a problem. On this slide you can see the message, change toggle switch or button cassette within 1 minute. And dispenser protection configuration is physical. So, The firmware was downloaded, but it's not interesting for us as money withdrawal. Unfortunately, withdrawing the money is also a difficult task. Just look at the graph of function that checks withdrawal packet's validity. Surely with the decompilator it would be easier. The stack controller is that part of code which makes bundles of banknotes, checks the hardware, and many other mechanisms that get stuck. It also checked the ATM was tampered. It was difficult to analyze the stack controller without any peripherals. In fact, my colleague didn't want to analyze the stack controller at all. One look at the validate command function was enough to close its code and never to return to it again. But after we analyzed all codes, we had to return to the stack controller function. The problem was not only in its code size. The captured traffic that contained this command was encrypted. Here I want to say a few words about stack controller command itself. The first thing, we must specify the cassette numbers in which banknotes are stored. Cassette numbers are virtual ones and they can be reassigned, but in our case their numbers were equal to real cassette's location. On this slide you see that we asked the first cassette to give us 5 banknotes. If your cassette doesn't have the required amount of banknotes, the dispenser will send you an error. After we worked out the stack controller works, we decided to perform the first real withdrawal. Vladimir assembled a firmware with a fixed secure command function, which I have mentioned before, downloaded the firmware into dispenser and sent the stack controller's withdrawal command. In the response, we received a message about hardware error. There was many versions of why that would happen, ranging from a malfunction of ATM hardware to additional checks we have not performed. That day, we didn't get any money. We were afraid that dispenser was completely broken. A bit later, we found the clear main transport command, and we decided to use it just because its name looks interesting. This command is necessary for the money withdrawal process to clear, and we need some related things. Unfortunately, the real packet was captured, so only the Python hex dump on the slide was presented. After we made the second withdrawal try using clear main transport command, we got the money. After a long and painful search, after a dozen times breaking controllers, we managed to make withdrawal. As a result, we have succeeded to execute our code by passing the encryption, worked out stack controller principles to understand how ATM cash withdrawal occurs, and have also learned about how to initialize all the mechanics correctly. Let's see the demo. Some preparation, as I mentioned before, we need to exchange initial keys with the host PC controller of ATM. You can see words I mentioned before. And then it's authenticated, and it's secure. Protection level is physical. So let's start. We take a USB cable from PC, connect to our laptop, and started our proof of concept code. We have no optimization of this process because it's proof of concept, and not a real attack. Now you look at the firmware uploading. It requires some time, and the speed of video increased a little bit. Also, you can see timestamp on the bottom on the screen. Now we need to reboot to new firmware and init all mechanical hardware. And then send clear main transport command to clear all the things inside ATM and transport bills to reject cassette. And then we send withdrawal command. And we take money for 4 minutes with no optimized code. So this is a demonstration video that occurs our attack was successful. After we assured ourselves that vulnerability really allows to execute arbitrary code and issue the money, the report was sent to NCR last December. The research was done on the basis of S1 controller, but later it was confirmed for S2. The presence of vulnerability was confirmed and the fixes in the February security fix. As you can see, there are 2 CVE numbers for these vulnerabilities. They are related to S1 and S2 controller. Also, NCR issued white paper related to these recommendations for updating. Thank you for listening and watching. And now ready to answer questions in the wrap room.